Okay. Well, thank you very much. This is Russ Hemley from University of Illinois, Chicago, currently on the West Coast. I apologize for not being there in person, but I had committed to a meeting here in La Jolla prior to this. It's a pleasure to take part in this timely workshop, and it's also a pleasure to be a part of this series of talks with my fellow experimentalists. Although today I'll be talking about theoretical work as well as experimental work. And one of the important points I'd like to make throughout the talk is the importance of the synergy in experiment and theory, and very much goes to the overall theme of this workshop, challenges in designing room temperature superconductors, not just making them, but designing them. So the outline of my talk is shown here. Start out with some general background and then move into sort of the context in terms of metallic hydrogen. I believe a few words were said about this earlier. Then move to a short discussion of binary hydrides, ternary systems, and then the challenges of low pressure stability. So again, the themes, this is about hydrogen and extremes. And again, I come back to the synergy between computation and experiment, theory and experiment. And this is really a wonderful example of materials by design. Really remarkable, really, in modern condensed matter physics. So just with an overview of the kind of work we do, we're interested in high pressure experiments, both static and dynamic compression experiments, but most of our work is in the static field. And there we use diamond anvil cells, which of course are very valuable because they allow us to probe materials using a wide range of characterization probes, not the full set that is available for ambient pressure studies, in particular for superconductors, but still quite an impressive range that continues to improve in sensitivity, resolution, and accuracy with each passing year. And we also use large radiation facilities for measurements on these materials, X-ray and infrared synchrotron measurements, as well as laser facilities and neutron facilities. And I'll be talking primarily about the X-ray work that we do. And also, again, coming back to computations, we're also involved in computations. A lot of this work is done in collaboration with our excellent theorists in the field, using various types of density functional methods, but extending them to include path integrals, quantum Monte Carlo. And the important point here is using these techniques in combination with modern structure search methods, which have been truly revolutionary and very important for this field of room temperature superconductivity. So a little bit about pressure and superconductivity. Of course, there's a deep history here going back to the very first effects of pressure or stress by Camerlingionis on tin and indium back in the 20s. We now have the superconducting table of the elements shown here, a number of elements turned into superconductors, even gases turned into superconductors under pressure. And before the hydrides, we have the record in the cuprates under pressure of the mercury, barium, calcium cuprate work that was done in our lab many years ago. The work that has been quite important experimentally for us in the hydrides is getting up into the megabar range. So an important breakthrough in the late 1990s was the first measurements on elements, superconductivity, TC measurements as a function of pressure up into the megabar pressure range. And this is just an example of a few: niobium, sulfur, and boron, using magnetic susceptibility methods, as well as electrical conductivity methods. Discovering these new superconductors or measuring high pressure properties, for example, of niobium, and looking at transitions such as Lifshitz transitions in these materials as detected by the variations in TC with increasing pressure. But of course, the work on hydrides and hydrogen-rich materials goes back to the celebrated calculation by Wigner and Huntington that hydrogen under some degree of pressure would possibly become a monatomic alkali-like metal. And then this was followed many years later by Neil Ashcroft's prediction, along with Vitalik Ginsburg, that this material could be an intriguing superconductor, perhaps at a TC well above room temperature. This was just based on simple BCS arguments for a conventional electron-phonon coupling superconductivity. little bit about hydrogen because it sets the stage for the work on the hydrides and the hydrogen-rich compounds. A phase diagram shown here in the lower right, up to 350 GPa. This has been extended to much higher pressure, but it shows the marvelous physics that has been uncovered in just pure hydrogen over the years. These interesting structures, this ionic phase or phase 3 and this graphenic phase, and intriguingly, these structures were predicted by Chris Picard many years ago. So here, even in the case of pure hydrogen, theorists were leading the way and giving us guidance as to what kinds of phases we were observing under pressure. This graphenic phase is quite intriguing because it has parallels to carbon graphene. So some of this interesting physics you see in carbon graphene maps over into this intriguing phase 4 of hydrogen. We've also looked at other phases in our own theoretical studies. We've predicted that another phase with a CMC4 structure could be a very interesting semi-metal, a topological semi-metal with surface conductivity. We think this is important because it could possibly be relevant to interpretation of experimental data, which may be controversial. So what can we say about the properties of this material? Just very briefly, we focused on optical studies over the years, and the very first observations of so-called black hydrogen go back to 1989, when we found in heterogeneous samples at pressures above 200 GPa. At that time, we couldn't measure pressure above 200 GPa, but we estimated it was of some pressure above 2 megabars. That one has this band gap closure. We could not determine whether it was a metal or not, but there was evidence for band gap closure. We extended this with direct optical observations as well as infrared measurements to 360 GPa. In fact, this is phase 3, showing the very wide stability of this phase, a C2 or C structure that had been predicted and is consistent with theoretical work and more recent work. Subsequent to this, and in the recent years, my colleagues have gone to higher pressure and with optical measurements found evidence for reflecting hydrogen, this possible atomic metallic form at something like 500 GPa, and then extending the synchrotron infrared measurements that we conducted earlier to higher pressure. The group of Paul Lebert found evidence for actual closure of the gap at higher pressures than we reached in our earlier studies. And this is also complemented by electroconductivity measurements by Mikhail Ermetz's group. So we have now this interesting plot of band gap closure as a function of pressure, theoretical calculations, as well as all the available experimental data from optical measurements, showing really some degree of convergence, the possibility of a semi-metallic phase before becoming fully metallic in an atomic phase. There are controversies as to whether or not there are intermediate phases, whether there is a phase field of stability of the semi-metallic phase, but there is some degree of convergence now between theory and experiment and among theoretical groups for the behavior of pure hydrogen under pressure. This is also quite relevant to some work that was done in collaboration with Jiangbin Chen's group, as well as Yanmin Ma's group, on the effect of anisotropic strains. And this actually can help resolve some of the controversies in terms of where the pressure onset is in this material for the metallization or for band gap closure. What we found in these calculations that were just published is that, in fact, there is significant strength in these materials at high pressure, as shown here in these plots in the middle, the shear strain and compressive strain that's supported in these diamond cell experiments as modeled in this TFT calculations. And this anisotropic strain can lower the effective pressure of the onset of metallization in the system, as shown in the bottom plots for shear strain and anisotropic compressive strain. So this gives us also the possibility that there is superconducting metallic hydrogen in the molecular forms that are building on the earlier work for hydrostatic compression, that could be possible stress-induced superconductivity below 300 GPa in this system. And this is just shown again using conventional BCS arguments. And here's the calculation of the superconducting gap as a function of temperature. So at higher pressure, of course, we're interested in the behavior of the atomic form and potentially higher TC in these phases that have not been fully characterized yet, although there are indications from conductivity and optical measurements for these phases. But this goes to some very interesting physics that continues to be of interest to us, and that is the possibility there may be altogether new kinds of behavior at very high pressures, the possibility of a superconducting superfluid as proposed by Ashcroft and co-workers, in addition to the possibility of atomic metallic form and a solid forms of superconductivity. So big open questions in this system. So now let's turn to the problem of the hydrides and the exciting results there in compressed hydrogen-rich materials. The problem, of course, in compressing hydrogen to very high pressure and looking for dissociation is the strength of the covalent bond. It's a very tightly bound molecule with this very spherical charge distribution, as you can see here, giving rise to this idea that it's really a very tenacious halogen if you view it as a halogen system, or it's a reluctant alkali that does not want to become a true alkali until we reach very high pressure. The point that Neil Ashcroft made in a very nice paper he wrote in the mid-1990s. But prior to that, he proposed, along with his student A.U. Carlson, there could be approaches for reducing the insulator metal transition in hydrogen, basically by destabilizing this very strongly covalently bonded system, putting electrons in the antibonding orbitals of the molecule, either by impurity stabilization or chemical doping, or by some kind of electron hole pair creations, such as by irradiation with some kind of light or X-rays. And this gave rise to a later, more detailed study of just the chemical compression aspects and what has come to be known as chemical pre-compression, which sort of underlies the idea behind how we think about the hydrides and superhydrides that have been observed now experimentally and are being predicted in various theoretical calculations. So the work of A.E. Carlson and Ashcroft years ago prompted us in the early 90s to start looking at mixing additional elements in with hydrogen to look for some of these phases. We did a number of studies up to sort of the 50 GPa range, and we uncovered this vast new chemistry that we called van der Waals chemistry, van der Waals compounds that form. And here are examples in the methane hydrogen and hydrogen sulfide system. And these are now very interesting because these are precursors for some of the high pressure phases seen in the CSH system. Of course, subsequent to this, structure search methods started being applied to these various systems, and in particular to the H2 system, and very important calculations that we're all aware of were conducted that predicted that these could in fact be very interesting atomic-based hydrogen rich superconductors, in particular this H3S structure that has a TC of 200 Kelvin. And of course, this work was confirmed rather quickly by my colleague Michael Ermetz and his group with measurements, very nice measurements of the pressure dependence of this, as well as the isotope effect, indicating this is indeed essentially conventional superconductivity. And the remarkable finding that this is in very good agreement, both in terms of the structure, the TC, and the range of stability that came out of the DFT calculations. But what about higher hydrides and still higher TCs? We became interested in this problem ourselves and focused on the rare earth systems, thinking that the rare earths might be able to supply those extra electrons needed to destabilize the hydrogen molecules at high pressure and give you lower pressure stability of systems that could look like metallic hydrogen, and also perhaps with higher TCs than those p-block elements. So here are some convex hole plots for yttrium hydrogen and lanthanum hydrogen. The work was done by Hanyu Liu in our group, and one found in these calculations is very intriguing, very hydrogen-rich materials that we called superhydrides that is with hydrogen stoichiometries greater than 6, so stoichiometries of up to 12, 1 to 12 in these systems. These are also interesting systems because in the case of the decahydride, of course, it has a very close similarity in terms of local bonding and topology to atomic metallic hydrogen extrapolated back to the lower pressures, that is in terms of the HH distances and the coordination. So this in fact looks very much like in the calculations, atomic metallic hydrogen, a doped atomic metallic hydrogen. And if you calculate the TCs using standard BCS theory in various types of calculations, including Eli-Ashberg calculations, one sees, in fact, TCs in the neighborhood of room temperature, this pressure dependence with the TC of the yttrium system being above that of lanthanum. An important point of this is that also, in addition to the simple idea that you have very high Debye frequencies or average frequencies and strong electron phonon coupling at high frequencies, at very low frequencies, we have strong electron phonon coupling, and the highest TCs emerge as you approach these dynamical instabilities that give the high TC, but also limit the stability, at least in these quasi-harmonic calculations, put a bound on the pressure dependence. So what about the experimental confirmation of this? We conducted a series of experiments right after these calculations. First of all, we targeted the pressure range that the theory predicted for the stability of the decahydrides for lanthanum, yttrium. Yttrium was much more difficult, but lanthanum was quite forgiving. And in the initial experiments, we found it was very easy to synthesize the lanthanum decahydride. You can see that from the clear X-ray diffraction. It was in remarkable agreement, slightly lower pressure than the predicted calculations, but essentially very good agreement with stability range that was predicted theoretically. And then we followed up with measurements of the conductivity, much more difficult than typical experiments because we had to do the laser heating in combination with the probes and this very small sample at pressures approaching 200 GPa, and ensuring that we transformed the sample under pressure without any chemical reactions with electrodes and other parts of the cell. We saw this remarkable conductivity onset beginning as high as 260 GPa in these, at 260 Kelvin at these pressures of sort of 180 to 190 GPa. This work was followed up within about 6 months by beautiful measurements carried out by the MINDS group, where they did many other types of measurements, including measurements as a function of pressure, the TC, and the isotopic shift and magnetoresistance measurements that largely confirmed what we had found earlier. And it's interesting that it took 6 years to confirm independently the work on the experimental work on H3S superconductivity. It only took 6 months in the case of lanthanum hydride. And that's a very important point that for this field is the importance of independent groups confirming one another, because there are many groups doing these kinds of experiments, and it's very important that multiple groups do these experiments and reproduce them independently. So of course, now we have a whole series of binary systems with very high TCs approaching room temperature in thorium, and now yttrium with different stoichiometries, praseodymium, and emerging systematics have come from these studies. A lot of this work has been done by Eva Zurich and her group, looking at all the systematics in these various systems, based largely on theory, but where we can compare with the available experiments. There's fairly good agreement for the binaries. These are electron doped hydrogen lattices, where there's charge transfer from the heavy metal to the sublattice, which consists of these cages, H24, H29, H32 cages, and the systematics that also emerge is that we have the highest TCs for lanthanum and yttrium in these systems, and this fall up in TC with increasing number of F electrons arises from essentially magnetic effects in the system. So these are very much high TC hydrides in the spirit of metallic hydrogen. This is a point that Warren Pickett has made in a number of papers. But another important point is, even though the electron-phonon coupling seems largely responsible as conventional superconductors, the fully quantum system affects the phase stability, and in more detail likely affects the pairing in the system, which is neglected in these more or less routine calculations that are being done now. So there's a need to extend the theory to make this a fully quantum system. I'll come back to this point at the very end of this talk. So we have a fairly good understanding for the binary systems, and until recently we thought that we basically had the maximum stoichiometry in the binary systems that produce this high TC, at least over the range of pressures that can be reached experimentally, so 300, maybe 400 GPa. But in some recent work that was conducted by the Gillen University group that I was a part of, and this work was just published in JACS, found yet higher TC and higher hydrides that we're calling extreme superhydrides in the binary system. And these have 36 atom cages, still higher hydrogen content. And for some of them, the cerium and the thorium, above 300 GPa TCs that are predicted using the same sort of conventional approach that's been used for so successfully for the other systems, TCs above room temperature. Was actually published in JACS just last week. So now I want to turn to some recent developments and to ternary systems, starting with the CSH superconductor. As I mentioned, this is the precursors for this phase are these van der Waals molecules or van der Waals compounds, and here's the beautiful TC plot from Ranga Diaz's group, showing the TC reaching some 288 Kelvin at 270 GPa. One can also plot these data in a different way without the sudden onset, and more or less a continuous plot. So some of the questions we are continuing to address as a community is the structure and composition, and of course the origin of the TC, and whether or not there's even a phase transition in this system or some kind of discontinuity in the TC. So let's start with the X-ray diffraction work in the structure. So we, in collaboration with Ranga's group, we looked at some of the very same samples that they had studied in their initial study of the high TC materials and measured X-ray diffraction over a range of pressures where equivalent samples show superconductivity. These were single crystal measurements conducted at the APS. These are images of the sample there on the left, and then some selected diffraction patterns. And from this, we're able to, in fact, show that these are continuous with the structures that we found earlier in the isolated systems, the high H2S, H2, and the CH4 H2 system. So this provides a way of understanding how this mixing of carbon and sulfur can result in some kind of phase that has carbon, sulfur, and hydrogen at higher pressure. It goes into an orthorhombic structure, and in the equation of state measurements shown here, we see this continuity with the low pressure EOSs, also show the various PV curves for the components. And so you can understand the compression in terms of the compression of the molecular and atomic components in the system. And here's a blow up the higher pressure range showing H3S as well as CSH, and this offset is due to the presence in some fashion of carbon in the system. In subsequent work, Goncharov and co-authors took measurements to higher pressure, samples that they independently synthesized, and found that this orthorhombic structure that we found collapses to form a cubic structure, something that we pointed out in this earlier study is likely to happen. And that becomes the basis for perhaps understanding the mechanism of TC in the system. So in looking at this, the mechanism, we took the notion that perhaps one has some kind of doping of carbon, and if you consider other dopants such as silicon or phosphorus, the same physics would emerge, physics and chemistry would emerge. But in the case of carbon and silicon here, what's needed is to somehow shift the Fermi level relative to the peak in the density of states that's just offset from the Fermi level in the pure H3S system. And this offset appears in basically all the band structure calculations for H3S. So this gave rise to a very simple idea of perhaps we could use the virtual crystal approximation based on DFT, where we have these hybrid atoms and we simply adjust the impurity content, do optimization of the structure, calculate the pressure dependence of the shift in the Fermi level, as well as then the subsequent electron phonon coupling and TC. And what we found is that the TC and the shift maximizes a very modest doping of just 4% in the case of both silicon and carbon. And when one plots the shift in TC with impurity content and pressure, one sees that one has this very striking increase in TC relative to H3S from basically 200 Kelvin to something like 290 Kelvin at only 4% in the case of carbon, and something very similar happens in the case of silicon. And to my knowledge, work on silicon the silicon doping has not yet been done. So this is an encouraging sign that perhaps whole doping by carbon is responsible for the TC, and this is more or less consistent with the available experimental data we have for the structure at these kinds of pressures. But what can we say about the carbon uptake and the actual local bonding configuration of the system? Because in this virtual crystal approximation, we basically smear out all of that information in this alloy type model. And in looking at this, we built on some earlier work that was done with collaborators at Jilin, as well as Eva Zurich's group at Buffalo. We found a new class of high TC materials, the so-called hydride perovskites, where one has stoichiometric substitution of methane in this case in the H3S lattice. It gives you very high TC. But this motivated further study of actually looking at doping and then asking the question, what's the nature of the carbon in the system locally? Do you have defects? Do you have methane-like structures, or do you have carbon in octahedral coordination by hydrogen, which is quite unusual? And in looking at this, some calculations that were just completed. This is work that was pioneered by or led by the Buffalo group in collaboration with us. We found that, in fact, pressure and chemical composition in this system can stabilize carbon in octahedral coordination by hydrogen, which is quite interesting. And there are parallels to the molecular ions that you can make and observe at ambient pressure. And we also looked at the shift in the density of states and the shape of the Van Hoeting singularity as a function of this doping in supercell calculation, so going beyond a virtual crystal approximation here. The full TC calculation has not been done for a supercell that is identical to what we have in the VCA model for optimal doping, but there's more or less consistency with the data so far. So we think we now have more or less a local bonding picture of the carbon in the system, although a number of questions remain, including the stoichiometry and defects around the carbon and so on. So this is very much still an active area of research, both experimentally and theoretical. So let's now move on to other systems, coming back to the lanthanum hydride in the work that we did showing high TC and lanthanum decahydride. We found in a number of experiments where we used ammonia borane as a starting material that one sees variable TCs or variable onsets of conductivity depending on the conditions of the synthesis. And these experiments were not complete for probe measurements. So we had to normalize the resistance. We didn't have a zero resistance state after the onset of conductivity. But nevertheless, onsets that varied from 270 up to 290 Kelvin. So this is quite intriguing. And at the same time, just a few months later, this remarkable prediction was made that perhaps TCs at room temperature or well above room temperature could emerge in these kinds of systems, in ternary systems. This work on lanthanum, lithium magnesium hydride in the LIMGH system, where there's this remarkable prediction of TC above 400 Kelvin in this highly symmetric structure. So the idea that perhaps room temperature superconductivity is just the beginning of perhaps a new field of hot superconductivity at much higher temperatures. So this idea that perhaps there is some role of the ammonium borane in the system and somehow responsible for the variable TC led to some calculations conducted that were very similar to the work that was done on CSH, where he asked the question of whether one has boron or nitrogen doping in the system, and how could this affect the TC? So he did a number of calculations very similar to what was done with CSH, looking at variable doping, calculating lambda, calculating the density of states, and we found interesting effects, not as large as those found for CSH, but we found that just 2% doping of nitrogen, for example, could increase the density of states at the Fermi level and the TC by on the order of 20-25 Kelvin in these very simple calculations. In fact, the maximum for nitrogen doping was about 1% at 240 GPa. So we have this other plot now for the doping level versus the pressure, and we see the TC increasing, which is sort of calibrated at 260 Kelvin going up to 288 Kelvin. So in agreement with what we see experimentally, at least a consistency argument that perhaps we have boron or nitrogen doping. In this particular case, it's the nitrogen that's most dominant. This work was also followed up with supercell calculations, just as the work on CSH, and the supercell calculations, again, were limited by the size of the supercells for the TC calculations, but we found for this supercell with 4 lanthanums, 39 hydrogens, and nitrogen gives a shift in TC that's more or less consistent with what we get in the VCA calculations. So at least some support for the virtual crystal approximation. And this also points out, and I'll come back to this, that higher TCs require some other compositions or different structures going far beyond the lanthanum H10 type structure. So as you probably heard, work done in collaboration with the MagLab team, and this was led by them. We did a very similar set of calculations. The goal of this, experiments, and the goal of this was to do careful measurements of magnetic field shifts and the Meissner effect. And in these experiments, we found that in this one experiment that was quite intriguing, an initial TC with a kink here, or evidence for some kind of behavior change in conductivity around 294 Kelvin, consistent with what we found in earlier experiments done with lanthanum and ammonia borane as the hydrogen source. And as you probably heard, when this was cycled repeatedly, thermally, increasing thermal cycling, cooling, and warming, this onset shifted to much higher values. So evidence for a conductivity onset above 500 Kelvin. Whether this is superconductivity remains to be proven. This was only one experiment that was cut short by COVID. Some diffraction measurements were done that are in support of the idea that we still have a lanthanum-based material, but clearly more work needs to be done to determine whether this is truly hot superconductivity. But I want to return to the LIMGH system and the predicted TC in this material, because this goes to the whole question of a mechanism and the need to go perhaps beyond what we're currently doing theoretically to really get at the nature of these materials. So if you look at this interesting material that was predicted by the Jilin University group with this very high TC, this very highly symmetric structure. It has these interesting tetrahedral sites, and some of them are filled with hydrogen, some are not. And this idea gave rise to the notion that there could be hopping between the sites, both in a classical sense at the temperatures of interest, that is where one has high temperature superconductivity, and at low temperatures due to basically quantum diffusion. So this motivated a series of calculations, both classical and path integral calculations, to look at these two effects. And in fact, what we find is that at high temperatures, one has diffusive motion, rather extensive diffusive motion, very much like what you see in many other hydrides that aren't superconductors. And this is in the vicinity of the TC, and at low temperature, you can see this persist in a sense in terms of quantum diffusion. So if you basically just freeze these structures and calculate the TC in a rather crude sense, make some assumptions for the charge on the hydrogen, you see a whole range of TCs that start at basically above 400 Kelvin for the calculation in the absence of any kind of diffusive or anharmonic motion or quantum effects, but going down to very low temperatures. So a range of TCs, and this just points out the need to go beyond the conventional theory and take into account at a fundamental level the nature of basically both the anharmonicity and the quantum effects in the system when calculating TC. So now I just want to turn to the question of low pressure stability in the last couple of minutes. This is a generalized phase diagram that motivates the thinking for doing a lot of this work in taking these interesting phases and looking for analog phases or stabilizing them to lower pressure, where we might have a dopant, we might have elements such as boron and carbon that could be structural elements that would preserve the kinetic or even thermodynamic stability of the system, some kind of heavier element that might provide the electrons to keep them hydride component in a monatomic state as well. So one possibility is to go to multinary systems, very complex chemistries, look at analog materials, for example, just simply replace the hydrogen with carbon. Some work we did a number of years ago showed that very high TCs could be found, at least in theoretical calculations, by replacing the hydrogens with carbon in the sodalite structures. And this material has kinetic stability or dynamical stability in the calculations at ambient pressure while preserving some of the high TC. But there also was the possibility of epitaxial growth, and then a new concept that we've introduced, the possibility of combining pressure and electrochemistry. So just on the one point regarding looking at compositional effects and looking at stoichiometric compounds, a lot of work has been done by Lilia's group and others looking at stoichiometric compounds that are stable at lower pressure while preserving very high T, for example, in the lanthanum boron hydrogen system. And this is work that we've done as well in collaboration with several groups. And this particular system, the LABH system, is interesting because one finds that LABH8 has fairly low pressure stability, a dynamical instability of around 50 GPa while still retaining fairly high TC. This is work that was found also by the Italian group. And you can again see that what's limiting this, but also maintaining the very high TC, is these dynamical instabilities that one reaches on decompression in the system. So it's very strong electron-phonon coupling that gives rise to the maximal TC. But now I want to turn to this new concept of combining pressure with electrochemistry. And this is work that we've done in collaboration with a group at Carnegie Mellon, where we asked the question whether or not we could somehow use an electrical potential along with pressure to enhance or change the stability fields of these materials. So one has the simple expression for the free energy, and the idea is that we need to suppress the hydrogen evolution reaction in this electrochemical cell, keeping hydrogen stable. And so to do this, one would put basically an electrochemical cell inside a diamond anvil cell and use an over potential to overcome the kinetic barrier for this hydrogen evolution reaction, and then tune this with different types of electrolytes. This is all theoretical work right now, but it's very intriguing. And if you apply this to the lanthanum hydrogen system, you produce a phase diagram like this, which is known as a Poor-Base diagram, where we have this potential as a function of pressures. It's a log scale, but it shows that the lanthanum hydride is stabilized by this increasingly negative potential at quite low pressures. So quite intriguing. This is work that was published last year in PNAS, and in some more recent work that was published this year in looking at the lanthanum magnesium hydrogen system, this in collaboration with the Gillen University group, returning to the LI-MGH system, looking at these phases plus the higher pressure phase with the very high TC, applying the same sort of methods. One finds that the first two structures, these were not actually reported in detail in the original paper that they published, are insulators, but this one here, the gamma phase is stable above 160 GPa in the absence of any kind of electrical potential. And it's a superconductor, as you can see there in that bottom plot, with this interesting pressure dependence of TC. And if you calculate the phase diagram for it as a function of electrical potential, you find that it's stable to quite low pressures. So a promising new route for these systems, stabilizing them at low pressure with electrical potential. So how would we do this experimentally? This is sort of a grand challenge for us, but the idea would be to take the high pressure electrochemical apparatus approach that Harry Drickemer developed in the 1980s, shown here in this plot in the middle, a 1 GPa apparatus where he was able to do high pressure electrochemistry, basically in the 10 kilobar range, but extended up into the 100 GPa range with diamond cells, and use basically various types of nanofabrication tools to build miniature electrochemical cells inside the diamond anvil cell. So this would be an interesting marriage of sort of battery technology, hydrogen storage material technology at high pressure. So a challenge for experiments. So just to conclude, here's what I've just talked about in terms of the lanthanum, the CSH and the H3S systems as a function of pressure, TC plot versus year, comparing the TCs we now have in these systems with the historical record going back to the original discovery of superconductivity, focused on the high TCs and pure hydrogen binary systems and more complex chemistries. The mechanism, and I've been arguing that one needs a full quantum treatment going, and this may be relevant to some of the questions in the literature about the nature of these conventional superconductors, and perhaps we need a new language to describe them. And I rather like the approach of calling these non-standard superconductors, superconductors nonetheless, but perhaps of a different flavor, because we're in a completely different regime of temperature, and we have a highly quantum and anharmonic system. And I made some comments about recovery to ambient. And then in words, here's just a summary of my overall conclusions. And without reading those, I'd just like to acknowledge a large number of collaborators, both experimentalists and theorists around the world, who are working together to make all of this possible. And I'd like to acknowledge these funding agencies as well. So thank you very much.